Okay, I joined. So what shall I do now? Once again, share participants. Shall I make you as a host? Yeah, just try and see whether you are able to do it. You are able to do, no? All right, yeah, okay. I will. Uh, yeah, I will just log out from here. Thank you, Naveen.
Uh, so good evening all. Let's start today's session. Today actually we'll be taking a quick look to our earlier assignment questions. If you guys have any doubt, you can put it up now. And then we'll be doing some problems out of the current week's content which have been taught to you. So let's start with our last week's assignment questions. So the first question started with which of the following scheme is not used for a wafer level bonding scheme? Uh, so actually the thing is it says that it is not used. So micro electric mechanical systems are used actually, which are MEM systems, you know, and sensors are just a type of that MEMS devices. So of course they are used, and micro electromechanical systems actually falls apart as per the question goes, and option D becomes the correct option here. So the next question asks for edge sensitivity. So in the last session, we have vividly discussed what edge sensitivity is, how many types of edge sensitivity are actually there. So edge selectivity, you can say, high edge selectivity or low edge selectivity is there. Now, this diagram at the corner of this current slide, you can see that these are the two etching systems. First one is for a low edge sensitivity system, and the second one is a high edge selectivity system. So when the edge selectivity is high, the substrate damage becomes low. Only the walls get etched, and the substrate surface remains negligibly damaged. Okay, so looking at the options, it is clear that option A, which says high edge selectivity, is necessary characteristic in micro machining, of course, for low substrate damage. If you use a low edge selectivity factor, then your substrate damage becomes higher. Okay, so option A is the correct option here. So next question asks for the type of photoresist used for forming the two type of features shown in this particular diagram on the right hand side. So we had discussed in details positive and negative tone photoresists. Now, you know that in case of a positive tone photoresist, the exposed area gets debonded once you develop it with a developing solution. Okay, so in option 1, you can see that the exposed surfaces or the exposed regions is getting washed away after developing. So first one goes for positive tone photoresist, and the second one similarly just the reverse of that becomes your negative tone photoresist. Okay. And the next question is about negative tone photoresist, which is SU8. The question asked what thing that SU8 photoresist doesn't contain. Now, epoxy resin, solvent, these are common terms in both the photoresists, you know. There is a photoactive compound which is there, but curing agents are not actually there in case of negative photoresists. Okay, so in the right hand side, you can see what are the main components of a negative photoresist given in detail. So a resin happens to be there, which is not sensitive to exposure actually. And then a photoactive component, of course, must be there for bonding or debonding. And then a solvent is there to make the resist actually bond or to the substrate or flow over the substrate, which can be used before the actual lithography process where we spin coat a particular resist material over a substrate. Okay, so without a solvent, that won't be possible, right? And then there is a developer, which you know is used to wash away the weakened portion after exposure. So curing agents is nowhere related, and option D becomes the correct option in this case. The next question was pretty much a straight question. It asked for the formula for resolution in case of photolithography, which is dependent upon your wavelength and distance between your masked, your hard mask, and then your photoresist layer. So in this question, you have in this formula, you have two variables in lambda and your S. S stands for your distance and lambda stands for your wavelength. So option C becomes the correct option again. And then the next question says, which of the following mechanical processes doesn't utilize abrasives? So abrasives, grits are used in case of uh, when these are used with water jet machining, it becomes abrasive water jet machining. So option A is there for the water jet machining with abrasives. Okay, so option B is a plain water jet machining. Abrasives are not included. In ultrasonic machining, abrasives are of course there, and in buffing also abrasives are there for finishing. So option B becomes the correct option. And then the next question asked, what about your lithography process? So it is whether it is additive or subtractive, depending upon your resist tone. It can be an additive as well as a subtractive, right? Now you first add a particular resist layer and then develop some part of the features depending upon your mask tone or your resist tone. So it is, of course, an additive and also an subtractive process at the same time. So option C becomes the correct option. Okay, so the next question asks for dry etching. So, dry etching happens through bombardment of ions, electrons or photons. Okay, you can have a look at the diagram in the right, and this has been taught to you in details too. So gases and liquids are not at all your etchant material. Your ions, electrons, and photons are the etchant materials, bombardment of which removes the substrate layers. Okay. So yeah, so your next question is about machining accuracy. And ion beam machining is an ultra precision machining. We have discussed it earlier, and the machining accuracy happens to be up to 1 nanometer scale. Now, there is one question about your conventions in case of bracket conventions in case of your crystallography. Now, you can refer to some explanations given at the bottom part of this slide. So there are different kinds of brackets, actually first, second, okay, then third brackets, okay, then there's fourth type of bracket when we have a number of crystallographic directions. Okay, then third bracket is used when we have a single crystal direction. We have to note a single crystal direction. Then curly brackets are used when we have a number of planes. When we are referring to a set of planes, and when we are referring to a particular specific plane, we use a first bracket. Okay, so here it says the direction in a crystal. Okay? So it is a single. It is asked about a single direction. So we go for the fourth option. We have a third bracket in Cartesian coordinate. Okay, hope it is clear. So that brings you to the end of your last assignment questions. If they are clear, then we'll proceed to some of the topics of your current week content and try to solve some problems out of that. All right, so let's start with your abrasive water jet machining process. Now, this is one concept about your mass loss, which is happening due to the action of abrasive action of your particles. Uh, so actually, initially, what happens is that the particles tend to embed into the material, and after that, after a little incubation time, your steady state erosion begins. Then the erosion factor which is there is actually dependent upon your particle velocity, okay, empirically. However, theoretically, your mass loss is related to the ratio of density to hardness of your workpiece and the kinetic energy of your abrasive particles, okay. Now, K, so this K in case of, so this K, uh, constant for glasses, it is 2 to sorry, there was a sudden loss of connection. So, issue of different kinds of materials. Okay. Now, depending upon this concept, we'll look Okay, so let's go to a problem. Depending upon this massless concept, you have a metal mask. Okay. So let's suppose you have uh, let's suppose you have a metal mask which is of 100 microns thickness. Okay. Then you have a hole pattern. Let this be a circular hole which is of 80 micrometers diameter. Then you have a glass specimen on which the whole pattern has to be cut out. Fine. So the glass specimen is there, in which you have to cut out the micro hole. Okay. The glass specimen is of dimension 250 cross 250 cross 1.2 cubic millimeters. Okay. Then you have been given air pressure, which is 2 megapascals, incoming velocity of stream which contains your abrasives as 150 meters per second. Further, density of aluminum is given as 3950 kg per meter cube, and density for your soda lime glass is given as 2500 kg per meter cube. Okay. So given these conditions, you have to determine the mass loss from the workpiece, the soda lime workpiece, while doing your abrasive machining, abrasive water jet machining. Okay, while making out a pattern which is of 80 micrometers diameter. Okay, through a metal mask which is your 100 micron of thickness. Okay. Now further, you may need hardness of the eroded material as 585 to the 10 raised to the power 6 kg per meter square. Okay. And then feed rate of aluminum abrasives be given as 0.02 gram per second. Okay. You can convert this to kg per second. It would come up to be 2 into 10 raised to the power -5 of kg per second. Okay, so given these things, you have to determine time required to get through a hole of the given die. So give it a try and then we'll discuss in details about the solution, right? So these are your data, and then you can take help of the mass loss equation, the formula to determine mass loss, which has been shown to you right now. Okay, you can take a note of this formula and then get the required result. Actually, let me write the formula for you. So the mass loss is given by K, the velocity coefficient, into ratio of density to hardness of the workpiece multiplied by kinetic energy of abrasive. Okay. So take help of this formula and just get down to the result. I hope you tried a little. So let's discuss the solution of this problem. Ask you to find out the time required to get it. And then there is a factor called feed rate given. So which is having, you can see here, it is having a unit of kg per second. So sorry about the interruption, guys. Seems to be a network issue today. So we'll start with the point where we left out. Okay. Uh, so from now we have to find out the time record to get a through hole of the given dia. Now considering that part, you first have to find out the mass loss, which you would get in terms of kgs, of course, and then this term is there actually, which takes the unit of kg per second, your abrasive feed rate. Now, if you divide your mass loss, a unit of kg by the unit of feed rate, kg per second, to get out what is called second. So you have to find the mass loss, right? So you it is given by actually, if you look at actually your weight factor. Thing by constant, your abrasive particle are aluminum particles. So we go for K metal into the factor density to hardness ratio of your workpiece, which is soda lime. And So guys, just give me a minute. Let's connect to my personal. So guys, give me a minute. I'll just connect to my personal hotspot. Otherwise, the Wi-Fi seems to be quite unstable today. Pardon me for this interruption. Okay, so Okay, guys. So we are talking about the mass loss factor and the way to find out the time required to get a through hole while abrasive water jet machining. So pardon me for the interruptions today. There is a huge network issue happening here at IIT Kanpur. Now, hopefully my personal network now works. So let's continue with this problem. So we are talking about the time required. So continuing with that, weight loss is given by this particular equation, and then in our case, we have seen here that the K for constant K for metals happens to be in the range of 2.3 to 3. So assuming K is 3, actually, we get the weight loss as 3 for velocity coefficient K, and the density to hardness ratio for soda lime, let be the density for soda lime has been given here as your 2500 kg per meter cube, and the hardness for the same is given as your 585 into 10 raised to power 6. So putting that into the equation, we have 2500 as density of soda lime, and the hardness being given by 585 10 raised power 6. Okay, and the soda lime is your workpiece here, okay, in which you have to get the through hole, and then you have the kinetic energy of the abrasive, which is given by half of mass of the abrasive particles, okay, which you have to find out from the given data actually, and then the velocity which is given is 150. You can see the velocity of the stream be 150. Now this mass you have to find out. How do we find out the mass? Now the mass is actually amount of your abrasive particles okay in kg. You can find that as a volume of, you can actually assume the amount of abrasive particles into action be proportional to the volume of the workpiece which have been removed. So you have to get a through hole actually, and the hole has a diameter of 80 microns. Okay, so the volume of hole multiplied by density of alumina. Okay, now volume of hole has to be found out as the area into thickness of the particular hole feature, micro hole required. So area is given by pi into radius of hole squared into thickness of the hole, which is given as 1200 microns. Okay, and then comes the density, which is given as 3950 kg per meter cube. Okay, so this is in microns. Now rearranging and getting all the things done, you have pi as 3.14, hole radius as 40 micron squared, depth of the hole as 1200 microns, and density in kg per meter cube as 3950. Now you change the microns to meters and you find out uniformity in your units and get the mass of the abrasive particles as 23 0.73 into 10 to the power minus 9 kgs. Okay, so the mass loss then becomes weight loss, which actually we have found out just earlier. And then weight loss divided by gravity, you gives you the mass loss. Okay, so you plug in the value of mass of the abrasive particles, total mass of the abrasive particles in this equation, and you find out that the weight loss becomes 3.4 into 10 to the power minus 9. Then gravity, let's assume it to be 9.8. So the mass loss becomes almost equal to 0.34 into 10 to the power minus 9 kgs. Okay. Now, given that, you have to determine the time required to get a through hole. So we discussed earlier that the time required can be found out by dividing your mass loss by the feed rate with the unit of kg per seconds. The mass loss has been found out to be 0.34 10 to the power minus 9. So your time required for making the through hole then becomes your mass loss, okay, divided by your feed rate. Okay, now plugging in the values, you have 0.34 10 to the power minus 9 divided by the feed rate has been given as 2 into 10 to the power minus 5 kg per second. Okay, so it becomes 10 to the power minus 5 kg per second. So your time comes out to be almost equal to 1.74 into the power minus 5 seconds. Okay, you can look at the calculations back home if the concepts are clear. So having said that, let's proceed to another question from abrasive jet machining. So this question is about the concepts called as mixing ratio and your ratio of abrasives to carrier gas density. Okay, or you can say mixing ratio given by your volume. Let me write that down for your convenience. So take care of two things. Okay, one is your mixing ratio and another is mass ratio. Okay, now the mixing ratio is actually the volume of your abrasives in case of abrasive water jet machining to the volume of your fluid. Okay, maybe that is water, maybe that is gas in case of maybe that is air in case of abrasive jet machining. Okay, if that is not water, so whatever, if it is gas, then let's suppose gas. If it is water, you can take it as water. So the amount of or you can say the volume of abrasives to the volume of gas. Okay, and then mass ratio is actually the mass of abrasives to the total mass. Okay, so the total mass is abrasives plus gas. Now the question says the mixing ratio is given as 0.3 and the mass ratio have to be found out. Okay, the mass ratio have to be found out. Given that the ratio of density of abrasives to density of gas, the carrier gas actually is 15. So if these two things are known, you have to find out your mass ratio. Okay? It's a pretty simple question. Give it a try and then we'll discuss. Okay, so let us proceed with the discussions. Okay. So you have been given the mixing ratio to be 0.3 and the mass ratio has to be found out. Okay, density of abrasives to carrier gas is 15. So now you see that the mass ratio is given by the mass of abrasives to the total mass of abrasives plus carrier gas. Okay, now just rewrite these in terms of volume and density. You got volume of abrasives, okay, to density of abrasives divided by total volume of abrasives into density of abrasives plus, this is the total mass, okay? Volume of gas into density of gas. Now, if you rewrite that, then volume of abrasives, you can write it as 1 divided by 1 plus volume of gas, density of gas divided by volume of abrasives, density of abrasives. Okay. Now, what has been given to you is the ratio of density of abrasives to density of gas. Okay. So plugging in that value, you have 1 by 1 plus your volume of abrasives to gas, which is given as 0.3. Okay, so you put here because this is the reverse, so you take 1 by 0.3, and then the density of gas to abrasive to gas is 15, so the reverse becomes 1 by 15. So this becomes your 0.82. So I hope this is clear. If it is clear, then we'll proceed to 1 or 2 questions from ultrasonic machining. I think ultrasonic machining has also been taught to you in the current week. If it is so, let's proceed with 1 or 2 questions from ultrasonic machining process. Now the derivations and all the formulations has been taught to you in the class. So let me directly go to one question. So let us suppose that an ultrasonic machining has been carried out, okay, and you have been given that you have to get a hexagonal hole, okay, you know, a hexagonal hole. Let's suppose the side of this hole is 5 mm and the thickness is 4 mm, right? Now this thing has to be cut out, okay, and then through an ultrasonic machining processes. Okay, so let's the diameter of the grains D be given as 0.01 mm. Okay, this is your abrasive grain dia, and then you have a force of tool on grains, whose magnitude is being given as 3.5 newtons. The amplitude of this particular tool, ultrasonic machining tool, is given as 25 micrometers. Okay, so this is the force of tool upon grains, and this is
the amplitude of the tool. Now, the frequency, you know that the MRR in case of ultrasonic machining is also proportional to frequency. That the frequency of the tool motion be given as 25 kilohertz. Okay, and so this is your frequency, and the hardness of the workpiece is given as 6900 Newton per millimeter square. Okay, so this be the fracture hardness of the workpiece that it is made of tungsten carbide, WC. So given this data, you have to find out the time. You have to determine time t required to get the hole. Okay. So let's go and discuss the solution as well. So here you can see that the workpiece is a hexagonal one. Okay, so let's first start with finding out the volume of a hexagonal workpiece, because the volume of the workpiece will be required to determine the time. So let's first find out the volume of the hexagonal workpiece. So if you divide it in triangular forms, okay, you can see that if you divide it into triangles, you can see that there are 6 equilateral triangles. Okay, so find the total area of this hexagon. You have to just get the area of one equilateral triangle. Okay, so you know that area of an equilateral triangle is given as root 3 by 4 a square, where a is the side of the hexagon, or you can say the equilateral triangle. Then you have to just multiply it with 6 for 6 triangles. Okay, now you have to find out the volume. Okay, to find out the volume, you just have to multiply that with the thickness of the required hole, which is 4 millimeters. Okay, so you just multiply that with it, and you get the total volume of the hole to be found out as 2129 mm3. Now you go with the regular formulations of ultrasonic machining. So we have to actually get a hole into a workpiece, okay, through a grain which is of 0.01 mm dia. Okay, so let this be the grain. So you know that the grain is not a perfect sphere, rather it is having an irregular shape, and that is taken care of by assuming the dia to be actually proportional to square of dia. Okay, which has been found out experimentally. Let's suppose this be the radius of the particular plane, and it is actually d1 by 2. Okay, so that is indent the workpiece this way, and your t1 actually is proportional to your t square, which is the actual dia of the grain. So going with the formulations, you find out D1 first, okay, which is proportional to D square, and D is given as 0.01. So it becomes 0.01 squared, so almost equal to 10 to the power minus 4 mm. Okay. So proceeding, you have to find Z, okay, the number of particles making impact, okay, per cycle. So Z is actually given by the ratios, ratio of concentration, the concentration of your abrasives, okay, which in your case, let's take it to be half, okay. So what I meant to say is the number of abrasive particles, okay. So the number of abrasive particles to the total part of water, okay, in the, so let's take it to be half. So you multiply that with the ratio of area of your particular square, whatever you are having, in case it's a hexagon. So the hexagonal area is actually √3/4, the square into 6, isn't it? So divide it by your grain area, which is pi square by 4, which is assuming it to be spherical grain. So when you do that, you find out your Z value. Now you plug in the value of Z to the depth of your indentation, okay, which is HW. You know the formulation for HW, it is proportional to the force of tool on the grains, the amplitude of the tool, and inversely proportional to the square of grain dia, okay, then Z, which is your the number of particles actually making, or number of grains making impact, and then the hardness of the workpiece multiplied by lambda plus 1, okay. So lambda is actually the ratio of the hardness of workpiece to that of tool, okay. So let lambda, let's suppose it is 5, okay. So it is actually the ratio of your hardness of workpiece to hardness of tool. So given that you plug in the value of D1, which we have find out here, okay. So you plug in the value of D1 here. The force is given to be as 3.5 Newton. The amplitude is given. Z value we have find out just here. Okay. Now, then you find out the hardness value. The hardness of workpiece, I suppose, is given in the question as 6900 Newton per mm squared. So, given that lambda has been supposed to be 5, you find out HW. Okay. Now, once we have found out HW, supposing that the indentation, okay, so there is a particular indentation of the workpiece into the indentation of the grain into the workpiece. Okay. There is a particular indentation of the grain into the workpiece. So you can find out the total MRR in this case. You find out the MRR Q, assuming that the indentation is a hemispherical, is of hemispherical shape, and then the volume becomes your 2/3 I. Okay. capital D is your indentation dia, okay. D by 2 cube. Then the regular things are number of particles making impact and the frequency. Okay. So you replace the indentation dia D in terms of the dia of your grain and depth of indentation HW. Okay. To get D as equal to 2 of D1 HW. Okay. And by 2 gets you the radius Q Z min. So you plug in the earlier defined value of HW, Z frequency has been given. So just plug in the values and find out the Q to be, let's suppose the Q is your X, okay. The unit should be your mm³ per second. So once Q has been found out, you find out the time required to make the hole. It's Q, as volume removed divided by removal rate. So this is an mm³ and this is an mm³ per seconds. So when you do that, you get the time T, okay, and the unit is seconds. So that solves your question. I hope that is clear to you. So the only catch here was determining the area of the hexagonal feature to be cut out from the workpiece. So there can be different other features also given to you. So you must know to find out the volume, and the remaining process remains pretty much similar in whatever condition you are given. Okay. So yeah. So if that is clear, I hope there are no doubts. If that is clear, let's proceed to one more question from ultrasonic machining. Okay, so that question, it asks that you have been given. Sorry. Okay, so let's suppose that you have been given a tool whose material has been changed. The tool material is actually changed from copper to SS, stainless steel. So then you have to determine the percentage reduction in time of machining. Okay, of course, it is I'm talking about ultrasonic machining. So it's a simple question. So actually, if we go to the solution, you know that the MRRQ, okay, is actually proportional, inversely proportional to your 1 plus lambda, the ratio of hardness of your workpiece to 2, okay, and it is raised to the power of 3 by 4, right? So using this concept, you can see that from when it is changed from copper to stainless steel, right? So QC divided by QS is actually given by 1 plus lambda for stainless steel to the power 3 by 4 1 plus lambda for copper raised to the power 3/4, which is almost equal to lambda s by lambda c raised to the power 3/4, right? Now your lambda is again directly proportional to your hardness, isn't it? So for that case, you can still say that lambda s by c to the power 3/4 is again proportional to a hardness of copper by hardness of steel to the power 3/4. Okay. So if we assume that hardness of steel with thrice is that of copper, you know that copper is a softer material ductile, more ductile in terms of when compared to stainless steel. So if we assume that to be thrice the ratio of hardness of steel to copper, then 1/3 raised to the power 3/4 becomes the ratio of your material removal rate, ratio of copper to steel. Okay, so of course you know that the time of machining becomes inversely proportional to material removal rate, isn't it? So higher the material removal rate, lower is the time required for machining. So you have to find the change in time requirements. So TC by TS, when you do that, it is inversely proportional to removal rate. So this becomes QS by QC, okay? And you can find it 3 to the power 3/4. That becomes almost equal to 2.27. Okay? Or you can say that the percentage reduction in machining time then becomes 56%. So that is, I hope this is clear. Yeah. You can ask me out if you have any doubts. So if not, then let's proceed to one more problem out of not a problem actually. This is an analysis of the process parameters in case of ultrasonic machining. If you have gone through the lectures, you must be knowing that. So let's talk about something called the effect of, or you can say the crushing of grains during ultrasonic machining. Okay? Of grains during ultrasonic machining. So let me ask you that what happens to be the MRR during USM with increasing grain dia. Okay? So if you look at the formulation for MRR in case of USM, So you can see that it is 2 by 3 pi 2 root over of dh by 2 q z nu. So q is directly proportional to d, right? Or you can say d to the power 3 by 2. So what then? So with increasing dia, the MRR should go on increasing proportionally, isn't it? So let's suppose make a graph between mean grain dia D and MRRQ. So it is directly proportional, isn't it? So it should rather continuously go on increasing with increasing mean grain dia. But that doesn't happen out to be, right? What happens is after a particular point of time, actually the MRR starts decreasing. Now, what is the reason? Here comes the effect of your crushing of grains. Okay, so after a particular point of time, the crushing tendency of grains increases. Okay, so resulting in a fall in this particular MRR. Okay, so this is your actual MRR variation with mean grain dia. Okay, and this is your theoretical variation. So considering that, you can have one more such thing coming into picture when you look at the variation of MRR with increasing feed force, okay, of the tool on the grains. So in that case also, you know that you can see from this equation that it is directly proportional. Okay, so here you can see h, the height of indentation of the into the workpiece, and the hw is again proportional to your feed force F, isn't it? So in that case, with increasing F, the MRR should go on increasing, right? But that is not actually the case in reality. What happens is with increasing feed force, if this should be your ideal case. This is a curve, parabolic curve, because it is proportional to 1/4 power. Your MRRQ is actually proportional to feed force raised to the power 1/4. Okay, so sorry, that is actually 3/4. So whatever it is, it should be a parabolic curve, but actually in reality what happens is after a particular point, so this is Q and this is feed force F. So after a particular point, actually what happens is the MRR starts falling more rapidly. So this is your Q actual. Why is that? The same case as the above one. With increasing feed force and the accumulation or the rubbing action between the grains lead to crushing of the grains or the abrasive grains, which actually results in decrease in MRR of the process. Okay, so yeah, so this is about your crushing phenomenon, and these two are clear. Then finally we'll look to clear on the last concept that suppose in case of an abrasive water jet machining, the dia of abrasives is changed or doubled. Okay, so D dash is twice of D. Then what should be the effect in MRR during abrasive water jet machining? So to know that, I hope you know how the MRR comes up in case of abrasive jet machining. So you actually equate the kinetic energy of incoming grains or grids to plastic strain energy of the workpiece. Okay. So when you do that, you know that the kinetic energy is half mv square and plastic strain energy is given by half into the force. Let that be the maximum force into the depth of indentation height, or you can say depth of indentation as HW. Okay. So similar to the USM process, you just replace the mass in terms of density and volume. Okay, and let B be the same, and then change the force to maximum force as the area of indentation into the hardness of the workpiece, or you can say the stress of the workpiece. This is almost equivalent to hardness. Okay, and keep the depth of workpiece remain as it is. Now, plugging in the value of D, which you know is twice root of DHW, you find out the height of indentation HW is root over of density by 6 HW into grain dia D or grid dia D. So after that, similar to your USM, you find the material removal rate be proportional to your volume removal per cycle multiplied by number of impacts. Okay. So that happens to be of 2/3 pi r cube, assuming that the indentation is a hemispherical indentation. Indentation area is a hemisphere. Okay, and the number of impact can be given by the ratio of mass flow rate. Okay, to okay, so that is for grains. All right. Now, once that is done, you find out that your Q is finally becoming 1.04 mass flow rate of the abrasive flow. Okay, and the velocity becomes proportional to 1.5, and then your density raised to the power 1/4, and workpiece hardness raised to the power 3/4. So if you change mass flow rate in terms of density and volume, suppose the mass flow rate be proportional to your going to dq. We are ignoring the constants here, so actually let mass flow rate be proportional to the density and the volume, which is proportional to dq. Okay, so in that case, The other thing remaining same. Yeah. So you can see that Q is actually proportional to cube of abrasive dia. So the question asked you that if the dia is doubled, what is the effect on Q? Right. So the other case, if the dia is doubled, you can find out that Q dash Q becomes 8, right? So the MRR becomes a cube of the original MRR, right? So yeah, this was you can say a simple derivation of the abrasive jet machining process. If that is clear to you, then we'll be concluding today's session here. Or if you have any doubts, you can shoot at on any of the two topics. Okay, so good night. Let's call this an end today, guys. We'll meet on the next problem solving session upcoming Friday.